Hello everybody, my name is Pashev, and today I'll be presenting our work called a Workflow-Centric AI platform for secure and transparent arbitration, authored by me and Silvia Gaftandzhieva from the University of Plovdiv, Brisi. So when we speak about our motivation and why we do this, it's about efficiency and access to justice, time saving on routine tasks, transparency gaps, security gaps, if you wish, lack of deep workflow modeling in many of the current ODR systems, and so on and so on. But the main motivation is in the first point, efficiency and access to justice. So what we did, our vision encompasses workflow-centric approach, process-first design, qualified digital signatures. Every AI action is a traceable script that can be confirmable. Procedural steps automated under human control, but automated with the help of AI. Even the very first process, first design, can be augmented and helped by AI, but the human is the one who takes the final decision if these improvement suggestions by the AI will be actually implemented in the current workflow design. Qualified digital signatures is something we are currently working on for our future work, because we need to use those stamps created by signing different documents and other data in these process files in order to store them in a future blockchain designed files, because using blockchain gives another security level, and that if data gets augmented or gets corrupt, those blockchain validation mechanisms, like checking by Merkle tree, for example, and etc., will suggest that some data in those files is manipulated not in the way it should be. So this is one thing for future work, and just opening the gates for this. Another one, efficiency problem. Many procedural steps in existing arbitration systems require much human work, because, for example, if a large amount of documents come to the arbitration court, there should be a large amount of humans that input those data in the fields in the file, and this is a very low in efficiency approach. So by combining this AI approach, we added additional parsing of these documents and automated OCR improvement with AI, and data extraction and automated extraction of this data and automated filling of data in the file steps, which reduced immensely the need of human work. But still, human can approve or disapprove data that AI-enabled software inserted in the steps. So, as I said before, all data remains under human control. We've got a multi-layered architecture. In the presentation layer, we have different apps like mobile apps, web interface, even desktop interface, administration portal, and etc., etc. In the middleware layer, we got session manager, event queue, metadata synchronizer, load balancer, request router, security manager, or what we call broker. And in the data layer, we got DB engines that are based on different base technologies. Some DB engines can be SQL based, other it can be our own object engine that is improved for this type of data. We got also hybrid engines. We have stored object engines that many PDF files are stored in the store object engines, and upon storage, automated data discovery process occurs for every PDF file, and automated extraction of metadata like entities, like concepts, and their relevance to the PDF file are automatically extracted from the PDFs using latest technologies, like, for example, BERT models and keybert library for Python. That is something quite used for extraction of concepts and different entities from the text. We can later use this extraction for other goals, like, for example, human voice recognition, which is also important during those arbitration sessions. So it's an ongoing work. For example, we use these Google-based models like Google Chirp for voice recognition. But in order to fine-tune the model, which words should pay attention more, we have previously extracted important data from those PDF files, and upon their relevance coefficients to the PDF files and data in the whole process, we then generate automatically those hints that can help, for example, Google Chirp to generate more and more efficient hints. There are sometimes errors, like, for example, errors from OCR, because some of those documents are subject to OCR process. And when we got errors from OCR, we are using onboard transformers networks to automatically detect such errors and correct hints before sending them to voice recognition models like Google Chirp. So I would say this is a very extensive work on computational linguistics fields. We got our own programming language, that is AMSG programming language, which makes use of those workflow identifiers or workflow IDs. So they're basically semantic references to different positions in those processes. And when thinking of what type of language and operator this is, it comes to mind the so-called flow programming languages. For example, if you are on step with type 7, you can use a workflow identifier to take data from that step backwards or forwards, or for example taking all of its satellite steps, and so on and so on. You can also chain these flow operators one after another. For example, you can take a step of type 3 backwards and then take all the satellite steps of this step number of type 3 in just a sequence of 2 flow operators. So basically this is a flow programming language, less or more. We can, for example, execute queries like all evidence before preliminary hearing, etc., etc. What is new is that we already use AI, for example, local lightweight model like Mistral, 7 billion parameters, to automatically generate these queries from human language. So a human can even use his microphone on the mobile app to make the model search for all evidence before preliminary hearing. This will translate the request to a sequence of our workflow identifiers that is then going to be executed by the system search engine. The search request is going to be sent to the broker. The broker is going to distribute the search request to all available and registered engines attached to him. And then our engine will send to broker its data that contains the results from the search query. The broker will then summarize all search results and send the result to the application server, which is going to send it to the UI, for example, the mobile app or another UI type. So this is more or less complex process that makes use of all system components. In this procedure, we got parallel procedure orchestration. The non-linear proceedings with concurrent activities, we got independent subprocesses with script isolation. We got merging results based on logical condition, and etc., etc. For example, some steps of critical importance can be stored in at least 3 engines, not just on one. Because if one engine somehow breaks, data can be then discovered from the other engines if data is much important and is somehow important. And that's why we get these parallel engines and metrics that synchronizes this data on engines. So the more important data is, the more likely it's to be distributed among at least 3 engines. The more new data is, it's also more likely it's to be distributed in at least 3 engines in this distributed architecture. And the older data is, the less likely it becomes for it to be distributed in these engines, because the older data gets, the less likely it's related to ongoing processes. So we got vector clock synchronization mechanism for tracking and event-based architecture for immutable audit trails. And we got rapid disaster recovery via event replication and step data replication, file data replication, etc., etc. AI modules are secure plugins. Even if someone tries to jailbreak an AI module, it won't harm the core architecture of the system. For example, AI models don't have access to the file data and the process data itself. It only has access to the metadata so that it can generate, for example, search queries and etc. etc. Or it has data to access to only public data that is anyway accessible to, for example, website visitors and so on and so on. So even if the model gets jailbroken, jailbreak it won't do harm. It will eventually generate destruction code in our AMSG programming language, but the code won't be executed. For example, the code to destruct data, it won't be executed due to insufficient privileges. So we have isolated those AI models as much as we can. And of course, this attempt for jailbreaking the model is going to be traced. The incident will be reported in logs and so on and so on. We've got transformer-based embeddings for documents. We got space-specific biasing for high accuracy transcripts. For example, all these complex process I told you for speech recognition involves one or two transformers-based AI models. We got integrated this into the secure AMSG programming stack, and so on and so on. This architecture has significant reduction in processing time. We use less human labor and more AI labor. We have improved adherence to procedural deadlines because there are many deadlines in those processes, and sometimes humans fail to adhere to those deadlines. We got high user trust via visible workflow explanations. For example, the AI model that is integrated into the system, like this Mistral 7 billion parameters, is often used by users to explain stuff. For example, current state of the process, and so on and so on. And this is the user interface of the web interface for arbiters, and it can be observed that it is quite intuitive. An arbiter can view his or her recent cases, recent activity. It can be easily reminded about pending actions. It can use AI assistants to ask questions, to search cases, to search steps in these cases, and so on and so on. I would say that this is only a first step to even more improvements. So the process is ongoing. And that's all from me. I'll be waiting for your, no doubt, interesting questions. And thank you for listening.